Okay, so hello everyone. The question which we'll be solving today is minimum cost, walk, and weighted graph. Okay, so this is today's LeetCode POTD, right? And we are just try to solve it. Right? So let me just read the question description for you. Okay, so before that, it is marked as a hard one, and the question number is 3108. So, what does the description says? Right, there is an undirected weighted graph with n vertices labeled from 0 to n minus 1. Okay. You are given an integer n and an array edges where uh, u of I, v of, like see, this is the edge I, ui comma vi comma wi indicates that there is an edge between. Suppose there's an edge between ui and vi, and the weight is wi, right? So it is a undirected graph. So like it's you can move from u to I and v to I. Okay, so it will also be like it will be something like this. So yeah, it's an undirected graph. Okay. So a walk on a graph like from here. This tells what is the walk, right? See, here is the explanation of what is a walk. Okay. A walk on a graph is a sequence of vertices and edges. Okay. The walk starts and ends with a vertex, and each edge connects that the vertex that comes before it and the vertex that comes after it. Okay. So like a walk is a like a sequence of, or we can say, yes, a sequence of vertices and edges. Okay, so if there is an, like suppose this is a graph, right? So like it's a sequence of, like the walk is a sequence of vertices and edges. Okay, so in other words, if the sequence of a, okay, so we were here, right? It is important to note that a walk may visit the same edge or vertex more than once. Okay, so this is an important point, right? Because suppose if this is a graph, if suppose this is a graph, we can go this way. Okay, we can again come this way and go this way, and we might go again this way, and suppose we come this way and we come back to this way. Okay, so it's not necessary that the edges and the vertices will only occur once, right? It's clearly this. See, this is a important point, right? This is important. It's also written. It's important that a walk may visit the same edge or vertex more than once. Okay, the cost of a walk starting at node U and ending at node V is defined as the bitwise and of the weights traversed during the walk. In other words, if the sequence of edge weights encountered, in other words, encountered, the walk is okay. The cost is calculated as okay. So like suppose there's a graph something like this. Let me just name it as an alphabetical. Like suppose there's a graph something like this. C and so if we like take the path from A to B to C to D. Okay, suppose their weights are 1, 2, 3, and 4. Okay, so it will also be like 1, 2, 3. And suppose if we come back to A again, okay, it will be 4. So the cost of walking, the cost will be 1 and 2 and 3 and 4. This will be our cost. Okay, it's written. See it. Then the cost is calculated as so denotes the bitwise and operator. Okay, so that's why we were doing and here, right? You are also given a 2D array query where query SINTI for each query. You need to find the minimum cost of walking at vertex S1, the starting one, and like the T is the ending one. If there is no such walk exists, return answer is 1. Okay, return array answer. Return the array answer where I denotes the minimum cost of walking for the query I. Okay. So this is the question. Okay. So now let me just explain it to you. Okay. Suppose like this is our graph. And this is the entire graph. Right. So tell me one thing that if we like okay, so let's just go through the example, then I will be explaining it. Okay. For the query 0 and 3, 0 to 3, okay, we need to go to 0 to 3. So to achieve the cost 1 in the first query, we need to move from the following edges 0 to 1, right? The weight will be 7, right? It's written out. Then 1 to 2, okay, it is 1, okay. Then again 2 to 1, okay, and then 1 to 3. So it will give us 1. How? Now let me just break it down here, right? Okay. So what if we write 7 in binary? Uh, like how we can write it? Like 4 to 1. 7 will be 1, 1 and 1. It will be 1 and 1. What if we go 0 to 1 and then we just go to 0, 1 to 3? So the path will be 7 and 7. So if you do the AND of it, what you will get? Which is equal to 7, right? Okay. So, but it's not minimum, right? As you can see. So what we did just erase it once. I did what we did. We have gone through 0 to 1, which is this, like 7. Then we let me just also write which steps. Then we have gone through like 1 to 2. Okay, so and of 1. Okay, then we go again back to 0 to 1, which will be 3. So what do we do this to the and at the fourth step we went from 1 to 3. So, okay, so this is our okay. So let's just try to compute this. So this is our 7 and this is our 1, right? So what will be the add of it? It will be 1, 0, 0. Okay, cool, right? Then for this we got 0, 0, 1, and then we compute this with this. So 0, 0, 1, 0, 0, 1, and we do AND of it, we get 1, 0, 0, 1. Okay. So again we got 1, 0, 0, 1. Right? Then we do again AND with this one. Like I am just doing the try run. If you like do it once, it will also give you the answer. Just for like to make sure how the things are happening and doing it like this. So what will answer? One we have one, then we have zero. Right? So this is our answer for this part. Okay. Okay. Uh, I think the things will be clear. So let me just like start giving the intuition how the things can be done. Okay, so this is what I was showing that is happening in this like the question. Tell me one thing that suppose we need to go from 0 to 2. Can we go? The answer is yes. 0 to 2. Can we? Yes. Okay. Can we go 0 to 1? Yes. And vice versa also. Can we go 0 to 3? The answer is yes. Okay. Can we go 1 to 2? The answer is yes. But can we go 1 to 3? Yes. We can go. Can we go 2 to 3? Yes. We can go. Okay. So it means that these all are in the same component, so we can go. Can we go 0 to 4? No. Can we go 1 to 4? No. Can we go 2 to 4? No. Can we go 3 to 4? No. Okay. Why? Different component. Okay. And why can we like go here? Same. Okay. Okay. So this means that if we are in the same component, we can go right. And so if you're in the same component, we can go right. Okay. So can we like see if you do the XOR like in this like oh sorry, if we are doing AND, okay, the more numbers you add, the lesser your answer will be. Okay, the AND never increases when new numbers are added. Okay, so suppose we want to go to 3, 0 to 3. Okay, we have or like suppose we have to go 0 to 2 to 0, right? We can go this way, we can go this way, and we can go this way. Okay, this is the way. Okay, and then after what is we can go 0 to 1, we can go 1 to 3, and we can come back to 1 to 3 to 1, and we can go here. Okay, or suppose if we go back to 2 and then we come back again and then we go to 0. Okay, so there can be paths found, right? There can be. So can I say that the like if we do AND of all these three, it will come minimum, right? And like that's what we can cover because we can go anyway, right? You can travel like the whole graph how many times you want. Suppose you can iterate it here the as much as you want, as much as you want. The number will decrease, right? And eventually will come here and do the AND. So you can like if we need to find the minimum and doing the AND of more numbers, gives you minimum. So you can say that we can select see make a conclusion here. What conclusion, right? What will be the conclusion? If the u we u and v are of the same component, we can just return the add of all the weights in that component, right? Okay, so that's what we can do, right? So this is what we are going to do. So it's easy, I guess. No, like it's not that much of a difficult. We have understood the question. So how do we find that if it belongs to the same component? How do we find if they belong to same? If you have studied this, you might have got this DSU, right? Yeah, that's our solution. We are going to use the DSU. Okay, so we know that the basic DSU or the standard DSU doesn't store the and uh, all the weights, but we can do it. We can just modify it. So yeah, the solution will be working for this also. Okay, and like suppose if they don't belong to the same component, we can minus one. Okay, so let me just go through the code and the things will be clear. Right? So you should be knowing DSU to solve this, right? So here's our DSU class. Okay, here is our parent, our answer, which will be storing, and okay, and here is the rank. We are using the rank in this question because without rank, the time complexity will increase and it will give you TLE because I solved it without using the rank and it did give me TLE at the last case, like the last test case. Okay, so you should be using it. Here we are just initializing the DSU, right? We are like parent size, then we have answer size. Okay, so one thing to note down that why we have used minus one, because if you do the minus one and with a number, it gives you number. It gives you the same number. Okay, so while doing the addition or subtraction, we use zero. Okay, so the minus one is like the zero for and. Okay, so we can think of that initializing the parent, right? This is the find parent function. You might be doing it, right? If you know DSU, okay, so like if you want to do this way, you should be knowing DSU, and DSU is important for the graphs. Okay, DSU is important, right? Okay. So what we're doing, we are just doing the and here, right? the and of the all the elements, like if they are of the same component, right? If they are of the same component, then the parent of u and the current weight which we got, we are doing the AND. Okay. This is important. Right? And like if you can see, if the rank of it's greater, we are doing the and of the parent u and the weight which has come, and this is the new component which are adding. Okay, so we are doing the and of it also, right? Okay, the same way we are doing here also and here also. Okay. So this is like how we solve the like implement the and in the case and operator, right? So we are just putting the elements into it, right? We have inserted the elements and here we are processing the query. Okay, we are finding the parents of both. If they are not same, it means that they are of different component, right? And here they are of the same component, so we are just putting the parents answer, like the answer. Okay, because like the parent will be the head and it will be storing the answer for the component, right? So yeah, and at last we can just return the answer. Okay, so okay, I can like just a second, I will be showing you the runtime. Okay, so I forgot to like put this screenshot. Okay, so as you can see, the code is running fine, and yeah, so that's all for the solution. Okay, so the question link and the code link will be in the description box. Okay. See, the DSU is important topic. Okay, so I must say that you should be trying this. Okay, DSU is very important. Is very So yeah, thank you everyone. Have a nice day ahead.